Hello, welcome to Amekadam's channel, and in this lecture we'll see another example of designing a maximally flat low pass filter. So maximally flat means it is also known as Butterworth filter. Cutoff frequency they have mentioned as 900 megahertz. They have mentioned R0 impedance for the source and load as 60 ohm, and they want attenuation at least 18 dB at 1.6 gigahertz. So we'll mention this data. So first I will write maximally flat. So that means it is a Butterworth filter. They have mentioned cutoff frequency. So FC is equal to 900 megahertz. Then they have mentioned R0 as 60 ohm. And they want insertion loss or attenuation of 18 decibel at F1, that is frequency 1.6 gigahertz. So first of all we will calculate the order of the filter, and for the Butterworth filter the order of filter is given as N, and that is given as log to the base 10 to the power a by 10 minus 1 divided by 2 logarithm of f1 by fc. So we substitute this data over here. So it goes like this: log to the base 10 to the power a by 10, so it will become 1.8 minus 1 divided by 2 log to the base 10 f1 1.6 gigahertz, and here fc is in megahertz. So I will convert this gigahertz into megahertz. So this will become 1.6 giga, means it will become 1600 megahertz divided by, so this is my f1, so I will write over here this is nothing but 1600 megahertz. Be careful about this conversion. Giga means 10 to the power 9, mega means 10 to the power 6 divided by 900. So I am not substituting megahertz, it will get cancelled, and this turns out to be, so we will substitute, calculate this one. So logarithm 10 to the power 1.8 minus 1 divided by 2 into logarithm of 1600 by 900. So it turns out to be 3.58. Now we want at least 18 dB attenuation, so we'll select the order of the filter as 4, next integer of this one, that is 4, so n is equal to 4. Now our aim is to calculate the coefficients of the filter, or you can say the lumped element values for omega c is equal to 1 and for R0 is equal to 1 ohm. So they are denoted as GK, and for Butterworth filter the coefficient G are calculated as 2 sine 2k minus 1 pi by 2n. So we'll type this thing where k is running from 1 to n. So in this case it will be 1, 2, 3, 4. So I will be calculating these values G1, G2, G3 and G4. So we have already calculated n, so n is equal to 4. So I will type this thing in calculator. So it goes like this: 2 into sine, here it is in bracket, I will write 2 into a, so alpha a minus 1, this bracket close. Now since your calculator is in degree mode, the pi has to be substituted as 180 divided by 2 into order, that is 4. So we'll calculate for k is equal to 1. So we'll type for calculate a is equal to 1. So it turns out to be 0.7654, correct up to 4 decimal places. And for G2, k is equal to 2, we get answer as 1.8478. Calculate for 3, it turns out to be 1.8478. For 4, it turns out to be, G4 turns out to be 0.7654. So we have determined the coefficients over here. Now we'll proceed for the designing of the low pass filter. So there are two possible solutions for every filter. So we'll proceed for solution 1. Now this is a low pass filter and there are 4 elements and n is equal to 4. So solution 1 comprises of first element as inductor in series, the second one capacitor, then inductor and then capacitor. So these values I will denote as L1, C2, L3 and C4. So I will be writing L1, C2, L3 and C4. Now we are designing low pass filter. So these component values will be directly proportional to the corresponding values of G. So L1 will be proportional to G1, C2 will be proportional to G2 and so on. Now we have to apply the impedance scaling. So for impedance scaling is applied like this. For inductor it will be multiplication by R0 and for capacitor it will be division by R0. Now we have to go for frequency scaling. So we'll dividing this by omega c. For all the component values it will be division by omega c. So we have already the values of these corresponding G. You have the values of R0. R0 is mentioned as a 60 ohm and omega c is 2 into pi into 900 megahertz. So I will be showing the calculation for a few elements. So here it will be G1 and G1 you have calculated as 0.7654. So we'll write over here 0.7654 into R0 as 60 divided by 2 into pi into Fc, and Fc is 900 megahertz. So 9 into 10 to the power 6. Be careful about the substitution. Most of the students do mistake over here. They substitute just 900 megahertz, but that is Fc. Here they for the frequency scaling they use omega c. So it is 2 into pi into 900 into 10 to the power 6. So we'll show this calculation. So it is 0.7654 into 60 divided by 2 into pi into 900 megahertz 10 to the power 6. So it turns out to be 8.121 nanohenry. So similarly you can calculate C2. The C2 turns out to be 5.446 picofarad. L3, actually one can modify this formula in the calculator. Instead of 0.7654, here G3 value will come and G3 is 1.8478. So it turns out to be 19.6 nanohenry and C4 turns out to be 2.256 picofarad. So we have determined all the component values for solution 1. So I will complete this network. So here you will have that resistance 60 ohm, source impedance. Here load impedance will be 60 ohm and here you will have a source. So that is about solution 1. Now we'll proceed for another option, that is solution 2. In solution 2, the first element I will consider as a capacitor in shunt arm because this is a low pass filter. The second element will be of course the series inductor, then again parallel capacitor and then series inductor. So here I will have C1, L2, C3 and L4. So we will be determining the values of C1, L2, C3 and L4. We are designing low pass filter, so the component values will be directly proportional to the corresponding values of G. So C1 will be directly proportional to G1, L2 will be directly proportional to G2 and so on. Now we have to apply the impedance scaling. So for impedance scaling is applied like this. For capacitor it will be division by R0, for inductor it will be multiplication by R0. And now we have to apply the frequency scaling. So for all the component values it will be division by omega c. So G1 was 0.7654 divided by R0 16 and omega c is 2 into pi into 900 megahertz. So 900 into 10 to the power 6. So if you calculate this thing, it turns out to be 2.25 picofarad. Similarly for G2, the G2 for C2 for L2, G2 is there and G2 is 1.8478 into 16 divided by 2 into pi into 900 megahertz, and this turns out to be 19.6 nanohenry. So if you observe carefully, the solution 2 is mirror image of the solution 1. So actually your C4 in the solution 1, which is 2.256, is becoming your C1. L3 is becoming L2 over here. So one can write C3, otherwise you can even calculate. It will turn out to be 5.446 picofarad and L4 is 2.25 picofarad. So we'll complete the design. So here you will have RL 60 ohm, here you will have RS 60 ohm, and you will have a source over here. So this is about the Butterworth, or you can say maximally flat low pass filter design. In the next lecture we'll see Butterworth high pass filter designing. Thank you.